Testing. Testing. All right, hello. We are working with C++ Chapter 8, and we're starting on page 358 with pointer expressions and pointer arithmetic. Pointer expressions and pointer arithmetic. C++ enables pointer arithmetic. That is, a few arithmetic operations may be performed on a pointer. Pointer arithmetic is appropriate for pointers that point to built-in arrays. Pointer arithmetic will be platform specific because each platform stores its data in different capacities. A double might require 8 bytes on one system. It might require 8 on another system. But float might require 4 bytes on one system and 8 bytes on another system. So we have to know your own system for byte capacity per data type. So pointer arithmetic, we can use the plus increment operator, the minus decrement operator, addition or our plus equals operators, and subtraction, the hyphen for the operation of subtraction, or hyphen equals. Figure 815 on page 359 displays for us a built-in array by the name of V and a pointer variable named VPTR, V pointer, indicating that it points to the location where the V built-in array begins at V sub 0. Notice that the location is referring to the memory location of 3000. V pointer can be initialized to point to V with either int where read from left to right, we're initializing the built-in array V to the V pointer, which points to an integer. Or we can initialize V pointer to the address of V, our built-in array name, at subscript 0. So V pointer is pointing to the address where our built-in array V begins at subscript 0. Two ways that V pointer can be initialized to point to V, the built-in array by the name of V. Adding integers to and subtracting integers from pointers. When an integer is added to or subtracted from a pointer, the pointer is incremented or decremented by that integer times the size of the memory object to which the pointer points. This is very exciting. We are dealing directly with memory assignment. So again, when an integer is added or subtracted from a pointer, the pointer is incremented or decremented by that integer times, that means multiplication. Integer times, multiply times the size of the memory object to which the pointer points. The number of bytes depends on the memory object's data type. For example, we might have VPTR plus equals 2. I remember that V is an integer built-in array. And integers require 4 bytes. So V pointer, we would assume that it's pointing to the beginning of V. So it would be at V sub 0. So our directions say that when an integer is added to or subtracted from a pointer, the pointer is incremented or decremented by that integer 2 times the size of the memory objects to which the pointer points. So we know that B sub 0 is at memory location 3000. So this is VPTR. Currently is pointing to the memory location 3000. We're going to increment it by 2, which means V sub 0 is what it's pointing to at 3000 plus 2 times we are storing integers with 4 bytes each. So this reports 3000 plus 2 times 4. Remember, multiplication has precedence over addition. 3000 plus 8. So we're looking at the new memory address 3008 will now be assigned to V pointer. Now, where is 3008? Well, 3000 is where the memory location is for V sub 0. It requires 4 bytes. 1, 2, 3. So V sub 1 is at 3004. It requires 4 bytes. And V sub 2 is at 3008. So sure enough, if I understand that V pointer is pointing to the address of V sub 0, which is 3000, and I add 2 to it and reassign it, I'll have its original value of 3000 plus the integer times the number of bytes. So we're going through each memory stored value of type integer in the array subscripted by 0, 1, 2, 3. Each subscript requires 4 bytes. So the pointer knows that it's assigned to an array housing integers at 4 bytes. So when we add 2 to the memory location, we're actually adding 2 times the number of bytes required for that data type to be stored. So we do need to know our data types and their required memory capacities. So 3000, 3004, 3008, and I think we set this up as a size 4 array. That'd be 7, 9, 10, 11, 3012 for the memory location V sub 3. So if we had VPTR as a pointer pointing to V, which is an array stored at memory location 3000, V sub 0, V sub 1, V sub 2, and V sub 3. Remember, we're off by 1, so it's 0, 1, 2, 3. Our size is 4. After we reassign V pointer plus equals 2, which is its current memory location at 3000 plus 2 times the number of bytes stored at each subscript. We're storing integers, 4 bytes each. It's now going to be assigned 3008. So I like to redraw my diagram using colored pencil. I'm just going to break that pointer's link and reassign it to the address of V sub 2. And sure enough, if we're storing integers, 4 bytes each, then that'd be 3000 as a starting point for V sub 0. We're storing an integer of 4 bytes, so this would be 3004. And subscript V sub 2 would be 3008. And subscript V sub 3 is stored at memory 3012. If the integer was stored in 8 bytes, just if, and we're looking at another scenario now, if the integer was stored in 8 bytes, so we have an array VPTR is pointing to the beginning element of array V. And V is at the memory address location of 3000, but we're storing integers of 8 bytes, so that'd be 3008 and 3016. So if we have V pointer arithmetic is reassigned plus equals 2, we would have its starting memory location of 3000 being reassigned to 3000 plus 2 times, remember our algorithm, when an integer is added or subtracted to a pointer, the pointer is incremented or decremented by that integer. Added or subtracted, we are adding the integer 2 times the size of the data stored at that memory location. And we're storing integers in this example, 4 bytes each, or 8 bytes each. So 2 times 8 is 16 plus 3000 would reassign VPTR to 3008. So again, my pointer is being reassigned, and it's now going to point to the memory location 3016. 2 times 8 is 16. It's going to be reassigned to 3016. The pointer now points to memory location 3016, which is the address at which V sub 2 is stored. The number of bytes depends on the memory object's data type. Your pointer knows the data type that it's referencing, so it knows the number of bytes required for each subscript within the array. If we have given VPTR as a pointer pointing to V at 3000 memory location, the beginning of the array at V sub 0, we have V sub 1, V sub 2, and V sub 3. And in this example, the pointer is currently pointing to V sub 4. And we're storing integers, 4 bytes each. So V is an integer built-in array storing integers 4 bytes each in each subscript variable. So V sub 1 would be at memory location 3008, 3012, and 3016. Notice we're counting by 4s for each maintained subscript storing an integer of 4 bytes each. So then our integer arithmetic, VPTR minus equals 4. Whatever the current value of V pointer is, we're going to subtract 4 from it and reassign VPTR. So it would produce we have VPTR is going to be assigned its current value. It is a pointer. Its current value is pointing to the address 3016. And we're going to subtract the integer 4 times the memory capacity required for storing each memory object at this location. We're storing integers, they're 4 bytes each. So that would be the pointer is going to be reassigned 316 minus 4 times 4 is 16. That's 3000. So VP pointer is reassigned 3000. The pointer now equals 3000. So it's now going to be pointing to, I'm just going to break that current pointer and readjust my schematic. It's going to be pointing to the memory location 3000, which is the memory address V sub 0. It'll be pointing at the integer memory location V sub 0, which is 3000. And we're storing a 4-byte integer there. Each of the following statements increments the pointer to point to the built-in array's next element. So using the increment operator, each statement increments the pointer to point to the next element in the built-in array that it's referencing. Each of the following statements decrements the pointer to point to the built-in array's previous element. Using the decrement operator, or either of these statements would decrement the pointer to point to the built-in array's previous element that it was referencing. Remember that there is no bounds checking on pointer arithmetic. So you must ensure, you and I, the programmer, we must ensure every pointer arithmetic operation results in a pointer that references an element within the built-in array's bounds. That is subscript 0 through its maximum size. Now, with pointer arithmetic, we could actually point beyond the beginning or the end of the array, and there's bytes stored in those memory locations. In fact, it could be another beginning of a new array, and it might be storing strings or characters or long doubles or floats. So that memory location immediately following the end of our array could be storing important data being managed by your system. So if we point to a location beyond the bounds, the beginning or the end of our array, we could be accidentally, or there are malicious acts that take place and reassign memory beyond the bounds of an array, and that can immediately disrupt your program. It can cause crashing or failure of a program, or it can certainly cause erroneous or inaccurate output. So it is very important that you and I ensure, as the programmer, that every pointer arithmetic operation results in a pointer that references an element within the built-in array's bounds. It's very exciting. We're managing memory, and we know that data resides in primary memory, and we're pointing to a specific location in memory, and at that location we're asking for its value to be stored and retrieved as a data object or an integer. We've seen examples of the integers, primarily doubles and so on. But we have to be careful that we are managing within our bounds, within their built-in array bounds. Subtracting pointers. Pointer arithmetic is meaningful only on pointers that points to a built-in array. Pointer variables pointing to the same built-in array can be subtracted from each other. So the key here is that we have pointers pointing to the same built-in array. I always draw out my schematic. And label. So we're storing 4-byte objects. Our first pointer is pointing to the beginning address of our array, and our second pointer has been assigned to point to the second element in the array, which would be at memory location 3008. So we could have X receiving the result of the 2 pointer and subtracting from it the PTR. Remember that pointers store memory addresses. So we have 3008 minus 3. And we're moving from 3008 back to 3002. That's 8. We are storing a 4-byte integer. So 8 divided by 4, that's actually 2 locations. So I move from 3008, 1, 2 locations. The number of built-in array elements from V2 pointer to VPTR1 pointer is actually 2 subscripts, 2 integers. A void pointer, you might see. A void pointer cannot be dereferenced. It makes sense because you cannot dereference a void pointer. The compiler does not know the type of data to which the pointer refers, so it doesn't know the number of bytes to return a value. A void pointer points to nothing, so it doesn't know if it's a 4-byte integer or an 8-byte double. It doesn't know how to return a value because it does not have the number of bytes that it should read and evaluate as a particular data type. Comparisons using relational operators are meaningless unless the pointers point to elements of the same built-in array. Again, the key word is same built-in array. Pointer comparisons compare the addresses stored in the pointers. A comparison of 2 pointers pointing to the same built-in array could show, for example, that one pointer points to a higher numbered element than the other pointer does. Relationships between pointers and built-in arrays. Built-in arrays and pointers are intimately related in C++ and may be used almost interchangeably. Pointers can be used to do any operation involving array subscripting. I'm on the top of page 362. Assume the following. Int b sub 5. So this is going to create a 5-element built-in array named B. Remember, the name of a built-in array is a constant. We can't change that during program execution. And it is a constant pointer. And assume int star bptr. This will create an integer pointer bptr, but it is not a constant pointer. we would have to include constant in our declaration. So the pointer, BPTR, which points to the first element, memory address of a built-in array B, is not declared to be a constant. The name of a built-in array is always a constant pointer. So assuming this, then the following is equivalent. BPTR is assigned. Remember that pointers store memory location. So we have to make sure that we're assigning a memory address to BP pointer. And we do that with our address operator. And the memory location of B sub 1 is the beginning of our array B, and we're asking for its address to be assigned to B pointer. So it also assigns the address of built-in array B to our B pointer. The expression B plus equals 3 will cause an error at compilation because it attempts to modify the value of the built-in array's name, which is a constant pointer. The name of a built-in array cannot be modified. So you will get a compilation error. Remember that built-in array names are actually a constant pointer to that memory location, the address at B sub 0. Page 362. Pointer offset notation. Built-in array B sub 3 can alternatively be referred and referenced with the pointer expression PTR plus 3. Here 3 is the offset. So our integer arithmetic with the pointer offset notation. And 3 is identical to the subscript. So this value is known as the pointer offset type of notation. Remember, notation is a form to represent something. We might have Minnesota West in bold. We might have Minnesota West in a color red, but it's still Minnesota West. So our offset is still our offset, but it is identical to the array's subscript that the B pointer is pointing to, and it's known as pointer offset notation, a way to represent and manipulate The parentheses are required because the asterisk operator has precedence over the plus, and we need to add first. So first, we're going to add 3 to the memory location stored at B pointer. So if B pointer is pointing to the beginning of the array at B sub 0, then plus 3, we'd now be pointing to B sub 3. The subscript is identical to our offset. So now we're asking for B sub 3. We want to return its value, the value of the data object stored at B sub 3 in our built-in array B. Note the address of B sub 3 is the same as the pointer plus 3. This is offset notation. Memory addresses are stored in pointers, and they know the size capacity of the data objects that they're pointing to. So we're pointing to the current value of B pointer, which we are assuming is at B sub 0. B sub 0 plus 3 would be B sub 3. This references the B sub 3 element location, memory location in the built-in array B, and this is telling us give me the address of the element B sub 3 in the built-in array B. Page 362. Pointer offset notation with built-in arrays names as the pointer. Remember, this is the array's name. It is a constant pointer and always points to the memory location of B sub 0. So B sub 0 plus 3 is the same as B sub 3. And so we're now asking for the memory address of B sub 3 to be returned and return to me the value stored. We're dereferencing. Return to me the value stored at B sub 3. Dereferencing B. B is the array's name. It is a constant pointer to the beginning of the array. So it's pointing to the memory location B sub 0. And we're now asking for the value stored at B sub 0 to be returned. So I have return the value stored at b sub 0 with the dereferencing operator. And BPTR is a pointer. It's pointing to the beginning of our B built-in array, and I'm asking for the value that's stored there. So B pointer is the same as B sub 0. So it's pointing to B sub 0 for a memory address location. And now we're asking for, at the memory address location where B pointer is currently pointing, which is B sub 0, return the data value or the data object dereference and return the value currently pointed to by B pointer. That would be the value currently stored at B sub 0. So now we're seeing kind of this relationship between pointers and the array subscripts. Pointers can be subscripted exactly as built-in arrays. For example, BPTR sub 3 refers to B sub 3, the built-in array using subscript notation. This is array subscript notation. And this is pointer subscript notation, both referring to the same thing, just different notations. A good programming tip: for clarity, always use built-in array subscript notation instead of pointer notation. So this is the preferred. Use array subscript notation rather than pointer subscript notation. On page 363, figure 8.17 code will demonstrate the four notations we've just described: array subscript notation, pointer offset notation with the built-in array's name as a pointer, pointer subscript notation, and pointer offset notation with a pointer, all to accomplish the same task, which is to display the four elements of the built-in array. It's a built-in array of ints by the name of B. So here's main and main. We're going to declare a 4-element integer array by the name of B and initialize it to 10, 20, 30, 40. So line 7. I'm initializing the array to contain integers 10, 20, 30, and 40 at their array subscripted notation locations. In line 8, I'm declaring a pointer to point to an integer and initializing the pointer to point to the built-in array by the name of B. Remember that the name of a built-in array is a constant pointer, so B pointer is being declared and initialized to point to the beginning of the array by the name of B. We're going to output built-in array B using array subscript notation. In line 11, we have array B displayed with array subscript notation and some formatting with new lines and such. So line 13, we're going to use array subscript notation. So we're going to iterate through the size of this array. I is going to be our counter initialized to 0. While I is less than 4, we're going to increment I by 1. We're going to output some nice display of the B named built-in array and subscript notation. And B's current value at B sub 1, 0, B sub 1, B sub 2, and B sub 3, when I is 4, we exit the loop. We're pretty familiar with array subscript notation, and we'd expect that 10, 20, 30, 40 is output in some nice display format using our 4 iteration looping. So our first example, the array B is displayed with array subscript notation, and we're outputting syntax to reference B sub 0 is equal to 10, B sub 1 is equal to 20, B sub 2 is equal to 30, and B sub 3 is equal to 40. Array subscript notation. In line 17, output built-in array B's values using array name and pointer offset notation. We have a nice title to our output, and we're using a 4 iteration to step through the array. For size T, offset 1, we're initializing offset to 0. We're going to allow offset 1 to increment by 1 through iterations in the loop while it's less than 4. We have some nice output display going on, and we're formatting the output, and then we're using built-in array using the array name and pointer offset notation. We're looking for, within parentheses, B plus the offset value. First time through it's going to be 0. So B is the name of the array. B plus 0 bytes would be actually referencing B sub 0, and we're asking for the dereferencing operator to return the value of B plus 0. So B plus 0 would be B sub 0, and we want the value at B sub 0. So we would expect 10, and then offset 1 increments to 1. B plus 1 would be referencing the array name plus 1 element, which would be B sub 1, and we're asking for the value that's stored at B sub 1. So we'd expect for 20 to be returned. Pointer offset notation, where the pointer is the array name. We're copying, we want to dereference B plus 0, the value stored at B sub 0. B plus 1 would be the array's name, location, and memory, plus 1 data object, which in this case is stored in B sub 1, and return the value stored there is 20. And dereference B sub 2 and dereference B sub 3. Line 28, we're using built-in array B using a pointer and array subscript notation to output. So in line 28, for size T, J is initialized to 0. It's our counter up 2, but not including 4. It increments by 1 as we reiterate the body of the loop. We're going to output some nice report type of generation, and then we're using B pointer sub J. So that is pointer subscript notation, B pointer sub 0. Well, B pointer sub 0 points to the beginning of the built-in array B. Its location is referencing the location of B sub 0. So we are asking for, with pointer notation, subscript notation, return B sub 0. And B sub 0's value is 10. Continue to iterate. J is now 1. Pointer sub 1, we're going to return the value stored in B sub 1, which is 20. Pointer J is now 2 is less than 4. Pointer sub 2 returns the value stored at point B sub 2. J increments to 3, it is less than 4. B pointer sub 3 is pointing to the built-in array subscripted B sub 2, and its value is 30. J increments to 4. To 3, I'm sorry, J increments to 3. We're looking for B pointer sub 3, which is pointing to B sub 3. We want that value returned, which is 40. J increments to 4. It is not less than 4, so we exit the body of the loop. And in line 35, we're going to output the array value elements using pointer offset notation. Iterating through the array for size t, offset 2 is initialized to 0, offset 2 is less than 4, will increment each time by 1 as we iterate through the body of the loop. We're going to output some nice report formatting, and then we're looking for BPTR plus the offset value 2 during this iteration in parentheses, and then we dereference it to capture the value stored at that location. So B pointer plus 0, B pointer plus 0 is B pointing to B sub 0. And now we're asking for the value stored at B sub 0, which returns 10. Next iteration, offset 2 is equal to 1. We want to add 1 to B pointer. Remember, B pointer is a memory address. Adding 1, it knows that we're looking at the next 4 bytes. And the next 4 bytes are stored beginning at B sub 1. We want to return the value stored at B sub 1, which is 20. Offset 2 is incremented by 1 to 2. B pointer plus 2. Remember that B pointer is memory address. It knows the data type that we're storing. We're storing integer values. So we're offset by 4. Your memory address increments by 4, moving us to the next subscripted value in the array, B sub 2. B sub 2 is a value of 30. We're asking for B sub 2. B pointer plus 2 would be the same as B sub 2. And we're looking for the value stored there, which is 30. Offset 2 increments to 3. B pointer plus 3, we're adding memory address. We know that B pointer is pointing to integer values. So we're moving to the next B pointer plus 3. We move to the same location now as B sub 3. And we're dereferencing that value. We want to know the value stored at B sub 3. which is 40. So let's run the program. We're looking at figure 8.17, and particularly we're demonstrating the 4 different methods to manipulate an array. Arrays subscript notation, using the array name and pointer offset notation, using a B pointer and array subscript notation, and using a pointer and pointer offset notation. So let's run the program. In subscript notation, we have B sub 0 is 10, so on. Pointer offset notation, where the pointer is the name of the array, which is B. Here we have B plus offset by 0. Well, that'd be B sub 0. And we want the value stored at B sub 0, which is 10. B is the name of our array, plus 1 would take us to the first element, which is B sub 1. We want to return the value stored at B sub 1, which is 20. The name of the array plus 2 would be the same as B sub 2. B sub 2, dereference it. We want the value stored at B sub 2, which is 30. And B plus 3, that's the name of the array as a pointer constant. Plus 3, we're looking at 3 data objects stored down from the beginning of the array. So that'd be B sub 3. We want its value with the dereference operator, and we'll output 40. Pointer subscript notation. Well, the pointer, B pointer, is pointing to the beginning of the array. So when it's pointing to B sub 0, the value there is 10. When B pointer is pointing to B sub 1, it returns a value of 20. B pointer sub 2 returns 30, and B pointer sub 3 returns 40. Pointer offset notation. Remember, the parentheses are necessary. We need to add first and then dereference. B pointer is pointing to the beginning of the array, plus 0 would be B sub 0. Dereference that, it's 10. B pointer is pointing to the beginning of the array, plus 1 object stored with 4 bytes would move us down to B sub 1. And we want to dereference its value, it's storing 20. B pointer is pointing to the memory address at the beginning of the array, plus 2 elements would take us to B sub 2, and we want to dereference and get the value stored there, which is 30. And B pointer pointing to the beginning of the array, plus 3 data objects that are stored in that array. That would take us down to B sub 3. The value pointed to at B sub 3 is returned with the dereferencing operator, and we get 40. Very, very exciting information as we're working with pointers and pointer arithmetic. All right, so now let's look at page 371. I'm going to work on problem 8.3. These are your self-review questions at the end of the chapter. So the answers are provided for you, but they're not worked out for you. So let's work a few of these together. For each of the following, write C++ statements that perform the specified task. Assume that double precision floating point numbers are stored in 8 bytes and that the starting address of the built-in array is at location 1002500 in memory. Each part of the exercise should use the results of the previous part where appropriate. So we need to work our way through A through J because B depends on A. And E depends on D, C, B, and A's results. So from that information, we're supposed to declare a built-in array of type double called numbers with 10 elements and initialize the elements to the values 0.0, 1.1, 2.2 through 9.9. Assume that the constant size has been defined as 10. Okay, so important to me is numbers is the name of the array, so it's a constant pointer. It will always point to the beginning of the array. The array, we have our subscript notation. And in this array, we are storing 8-byte double precision floating point numbers. So each subscript requires 8 bytes of memory capacity. And we've been told that size has been assigned to 10 as a constant, which means we have elements 0 through 9. We're also told that numbers as a constant pointer is pointing to the beginning location of numbers sub 0. And that memory location is 1002500. We are supposed to initialize the elements of the array the first number sub 0 value is going to be 0.0. And then numbers sub 1. Well, let's see. It's an 8-byte occupancy of contiguous memory bytes next to memory bytes. We started at 1002500 to store an 8-byte double precision floating point number 0.0. And we did that with a declaration. Double is the type. Numbers is the name of our array. It has a size, which has been defined and declared and initialized to 10 as a constant. And we're going to initialize, and I'm just going to continue over here, 1.1, 2.2, 3.3, 4.4, 5.5, 6.6, 7.7, 8.8, and 9.9. So if we have 8 bytes of memory required to store each of our data types, this is going to be 2000 or 1002501, 02, 03, 04, 05, 06, 07, And numbers 1 is going to be stored at 1002508. So our offset is 8 bytes to the next element. So each element is requiring 8 contiguous bytes of storage. So number sub 1 goes from 8, 9, 10, 11, 12, 13, 14, 15, and at 0025, that's 00. I guess it's 08. 5016, we have numbers sub 2 with array subscript notation. And at sub 1, we're storing 1.1, and at number sub 2, we're storing 2.2. And continuing with 17, 18, 19, 20, 21, 22, 23, and our memory location 1002524 is numbers sub 3. And number sub 3 is storing 3.3. How about numbers sub 8? Well, numbers sub 8 would be our beginning, starting from the beginning memory location, plus integer number is 8. Each element requires 8 bytes. So that's 1002500 plus 8 times 8 is 16. So numbers sub 8 is stored at 10025. 8 times 8 is 64. 8 times 8 is 64, 564. And at number sub 8, we're storing 8.8. So we have a schematic drawing. We have a declaration of an array by the name of numbers with a constant size of 10, and we initialized it to its values 0.0 and so on, with an object stored data type of double requiring 8 bytes for each element. Part B, declare a pointer in PTR that points to a variable of type double. Well, we have an PTR, and we want it to be a pointer to type double. How about that? NPTR, read left, right to left, is a pointer, and it's pointing to a double. Part C. Use a for statement to display the elements of a built-in array numbers using array subscript notation. Display each number with 1 digit to the right of the decimal point. So we're supposed to use array subscript notation. We want to display the elements of the array, so we're going to iterate through the array using the for statement. So we want to see out They're asking us for some output format attention. So I'm fixing the decimal point. I'm going to show the decimal point using a set precision of one place following the decimal point, and then going into my 4 iteration loop for size t. I is my counter variable. I'm going to initialize it to 0. And while I is less than size, I'm going to allow I to increment by 1 and begin the body of the loop. We're going to C out. We're using array subscript notation. So the name of the array is numbers, and allow it to iterate through 0 through 9. With some formatting and a trailing space after each number that's printed, and then end our loop. So subscript notation, numbers 0 value will be printed, numbers 1 value will be printed, numbers 2 value will be printed, and so on. D, write 2 separate statements that each assign the starting address of built-in array numbers to the pointer variable nPointer. Write 2 separate statements that each assign the starting address of built-in array numbers to the pointer variable nPointer. So nPointer stores the memory address of numbers. So we're deciding nPointer. We want to assign it to the memory address of the array numbers. So that's the address of numbers. And we want another example of assigning the address of the array numbers to our pointer. So we want nPointer to point to the beginning of the array numbers, so we could have it assign the memory address of numbers sub 0. E, use a for statement to display the elements of the built-in array numbers using pointer offset notation with pointer nPointer. So we're going to iterate through the array and display the elements. We're using a for statement to iterate through the array, but we're using pointer offset notation to reference each element in the array. So again, we can arrange for some neat output, well formatted, setting our precision to one place following the decimal point, and having that fixed. So we're going to use our for statement again to iterate through the size of this array. We can use j this time initialized to 0. While j is less than size, we'll allow j to increment by 1 on each pass of the iteration, and we're going to begin the body of the loop. Each time through, we're going to output okay. So we're using pointer offset notation. Here's our pointer and here's our offset. Built-in array b sub 3 can alternatively be referenced with the pointer expression b pointer plus 3. Remember, the offset is the integer value added to the pointer. The offset is also identical to the subscript of the array that b pointer is pointing to. So this in parentheses is known as pointer offset notation. So n pointer is pointing to the beginning of our array, plus 0 would allow it to continue to point to that memory location at the beginning of the array, which is b sub 0. And we want to dereference that and print out the value stored at b sub 0. In our case, numbers sub 0, sub 1, sub 2, as we iterate through the loop. So we'll be printing with pointer offset notation. Pointer is pointing to the beginning of our numbers array. The next time through, pointer is pointing to the beginning of the array plus 1, which is the same as numbers sub 1, and we're dereferencing numbers sub 1 and printing out its value. We iterate through the loop, iterating from numbers sub 0 through numbers sub 9. F. Use a for statement to display the elements of a built-in array numbers using pointer offset notation with the built-in array's name as the pointer. Use a for statement to iterate through the elements of the array and display each, using pointer offset notation with the built-in array's name as the pointer. So again, we're going to fix our precision, show point, and keep it fixed at one place following the decimal point. So using our for iteration statement for size t, we're using k this time, initialized to 0. While k is less than size, we're going to allow k to increment by 1 each iteration through the loop. The body of the loop we're going to output the name of the array, plus offset notation. All right, the name of the array is numbers. And remember that the name of a built-in array is a constant pointer. So we have pointer offset notation using the name of the array. So the first time through, we have numbers plus 0. Numbers is pointing to the beginning of the array, which is numbers sub 0. And we want to dereference numbers sub 0. Numbers sub 0 is 10, so we're going to output 10. The next time through, we're asking for dereferencing of numbers, but k is 1, which is the same as dereferencing. Numbers is the array's name. It's a constant pointer, plus the offset value of 1 would be the same as numbers sub 1. And we're asking for the value that's stored at numbers sub 1, which is 20, to be output. We'll continue to iterate through this loop and we'll have to dereference numbers sub 2, numbers sub 3, numbers sub 4, and so on. Use a for statement to display elements of built-in array numbers using pointer subscript notation with pointer in. Pointer. We're going to use a for statement again to iterate through the array, displaying each element of the array numbers. But we're going to do so with code using pointer subscript notation. So again, fix your format for output purposes, and then we're going to use our for statement. Initialize our counter to 0 while m is less than size. We're going to allow m to increment this time, and we're going to start the body of the loop. The body of the loop is our output statement using pointer subscript notation. So our pointer and pointer subscript notation. First time through the loop, we have pointer sub 0, which points to the beginning of the array numbers. We'll output the value there. Next time through the loop, m is 1. Pointer sub 1 is the same as numbers sub 1, and we'll print the value stored at pointer sub 1. Next time through, it's 2. Pointer sub 2 is pointer subscript notation, the same as numbers sub 2, and so on. H. Refer to the fourth element of the built-in array numbers using array subscript notation, pointer offset notation with the built-in array's name as a pointer, pointer subscript notation with end pointer, and pointer offset notation with end pointer. So we're looking at you referencing the fourth element of our array using our four methods of referencing an element in a built-in array. So first, remember that the fourth element of our array numbers the fourth element, 1, 2, 3, 4, is numbers sub 3. Remember, we're off by 1. So our numbers array begins at numbers sub 0 through numbers sub 9 for a size of 10 elements. So the fourth element is numbers sub 3. So we could reference that using array subscript notation. Pointer offset notation using an array name. As our pointer. So the pointer is the array name. Remember, the name of the array is a constant pointer plus offset notation, and we'd be dereferencing numbers sub 3 and printing the value stored there. The pointer subscript notation with end pointer and PTR with subscript notation would output the value stored at n sub 3 using pointer subscript notation. And pointer offset notation, we want to dereference our n pointer plus 3. So we want the value pointed to at numbers sub 0 plus sub 1, sub 2, sub 3. So this would be the same as n sub 3, and we want to access the value stored at n sub 3 using pointer offset notation. Assuming that n pointer points to the beginning of the built-in array numbers, what address is referenced by n pointer plus 8? And what value is stored there? Okay, assume that n pointer points to the beginning of the built-in array numbers. What address is referenced by n pointer plus 8? Going back to my schematic for my numbers array, and we are storing 8-byte double precision numbers. So each element requires 8 bytes. Each element requires 8 bytes. So when I get to number sub 8, what is the address referenced by n pointer plus 8? Well, n pointer is pointing to the beginning of the numbers array, 100250. So n pointer is a pointer pointing to the memory location 100250. Plus 8 elements, its offset is 8. So the offset, integer offset, is the same as a subscript. So that's the same as number sub 8. So n pointer is equal to, we were told to assume that it is pointing currently, n pointer's address currently stored is 100250 plus 8 is the integer offset. We have to offset it by the number of bytes stored in this array, and each element is requiring 8 bytes. So times 8 bytes. Remember, multiplication has precedence over addition, so we have 100250. Memory location plus 8 times 8 is 64. So that's 10025064. So the memory location referred to by n pointer plus 8 is 10025064. Remember, that's a memory location. Pointer store memory location. So assuming that n pointer begins with the beginning of the array and it's pointing to the beginning of the array, what address is referenced by n pointer plus 8? Well, the memory address referenced by n pointer plus 8 is 10025064. What value is stored there? We can dereference to ask for the value that's stored at 10025064, and it's 8.8. So what value is stored there? 8.8. The double precision data value stored at n pointer plus 8. Don't forget these in these questions. Sometimes there are 2 parts, so don't forget to complete both parts. Assuming that n pointer points to numbers 5, what address is referenced by n pointer after n pointer is decremented by 4 is executed, and what's the value stored at that location? So assuming that n pointer points to numbers 5, well, we know that the starting address of our array was at 1002500 plus 5, but each element requires 8 bytes, so we have to multiply by 8. That's 1002500 plus 5 times 8 is 40 for 1002540. So this memory address is 1002540. Now we have nptr minus equals 4. So we have the current value is 1002540 minus 4. That's I'm going to subtract the integer I'm going to manipulate times the number of bytes required by each item, which is 8. So 1002540 minus 4 times 8 is 32. That's 1002508. So the address now of n pointer, it's been decremented by 4 and reassigned. So it's now pointing to 1002508. And recalling our numbers array, n sub 0 was at 1002500 plus 8 to store a double precision number. So plus 8 would be number sub 1, and number sub 1 is storing the double precision value of 1.1. So what value is stored at 1002508? It's 1.1. All right, as always, return to D2L Brightspace to finish up with Unit 8, looking at your homework projects, tests, their due dates, and any extra details. And thank you very much. It's been a pleasure working with you through your CSCI2240 Fundamentals of Programming with C++. Please remember that this is an introduction to all of these topics, and you will revisit all of these topics and many more as you continue with your computer science career. Once again, thank you very much.